Hello everybody. In this video we're going to talk about limits at infinity. So let's just review the idea of a limit. All right? One of the examples I like to give for a limit is the idea of a balloon being inflated. All right, so we can keep track of the air pressure inside of a balloon. Suppose you connect a balloon to a hose and you have a pump and you start letting the air flow in, and the air pressure inside the balloon is going to build and build and build and build and build, right? Until, boom, right? The balloon pops. And so what we can ask is how much air pressure do we need until the balloon pops? What is that limiting air pressure that causes the balloon to pop? And the tricky thing about this problem is that you can't actually measure it. You can't measure that air pressure at the instant the balloon pops, because at the instant the balloon is popping, right, the balloon is peeling apart, the rubber has broken, the air is escaping, right? It doesn't make sense to measure the air pressure at that instant in time. You can't do it. At that point, the air is escaping from the balloon. It's no longer constrained. You're not getting an accurate air pressure reading anymore. So this concept of what is the air pressure at the instant the balloon pops is meaningless. But we still know what we mean when we ask, at what air pressure does the balloon pop? Right? So even though the value there doesn't make sense, even though the actual value of the air pressure at that instant in time doesn't make sense, we can still talk about what the limiting air pressure is. And what we're thinking about there is, as the air pressure builds and builds and builds and builds and builds inside the balloon, we can ask, what value is it getting close to? Right? What is that value that it's getting closer and closer and closer to that results in the balloon popping? That's the limit. That's the idea of a limit. And so this is an important example because it conveys the idea that the limit can be meaningful and have a meaningful value, even though the air pressure itself, the function that we're taking the limit of, can't actually be measured at that point, or it's not meaningful to measure it anymore. Right? So the limit can exist even though the value of the function does not at that particular time. All right, so, and this is, the very special thing about limits is it allows us to get at things that we can't measure at that instant in time or at a point in space. We can't actually measure the quantity there, but we can still talk about the limit. And we use limits to get the idea of a derivative, right? When we look at the definition of a tangent line, we do that by making little secant lines, right? We take on a curve, we take 2 points on the curve, and we just draw a straight line between the 2 points, right? And that's a line we can compute the slope of, right? And then what we do is we make those points get closer and closer and closer and closer together, right? And when we do that, we get slopes that get closer and closer and closer to a particular number. They're approaching the slope of the tangent line. If you actually let the points come together, you can't compute a slope, because to compute a slope, you need a change in y over a change in x. But if the x's are the same, you don't have a change in x. You're dividing by 0. And so the actual value doesn't exist when you let the points touch. But we can still talk about what the limit is as the points get close. And that's how we get the definition of a derivative, the slope of the tangent line. So limits are very important in calculus. And in this section, we are going to be talking about limits at infinity. All right, so we can be thinking about what happens over an infinite amount of time or over infinite space. So if I happen to have my water bottle here, my Gatorade bottle that I fill with water. And so to get the idea of a limit at infinity, I was thinking, suppose you put like a salty solution in here, a brine solution of 50% water and 50% salt, all right? And you stir it up, and so suppose it's dissolved. I don't know in chemistry if you can actually dissolve 50-50, but suppose we did, all right? Or we had some substance that we could do that. All right, so what I'm going to do now is I'm going to poke a hole. I'm not actually going to do it, but suppose you poked a hole in this bottle and started to let the solution drain out. All right, and then suppose we hold it under a spigot and let fresh water pour in at the same rate. All right, so since the solution's pouring out at the same rate fresh water's coming in, the volume of solution inside the container is not going to change. But suppose we kept it well stirred and we measured the concentration of salt over time. Well, if you do this, you should realize that it's going to get more and more diluted, right? Because you're pouring fresh water in and you're letting the well-mixed solution come out. So you keep adding more and more fresh water. And so it's going to get less and less salty as time goes on. So after, minutes, hours, days, weeks, we can keep measuring the saltiness. And you'll see, as you'd expect, the saltiness will just drop and drop and drop and drop. It will never get to zero. You can wait for months and you can still pick up a few molecules of salt in there, right? It'll never be completely pure water if you keep it well stirred, but it will be approaching pure water. It'll never actually get there. And so if we talk about the concentration of salt in the bottle as a function of time, the limit as time goes to infinity of the concentration would be 0. And so this is the idea of a limit at infinity. We let time or whatever quantity we're measuring things with respect to go to infinity and ask, what is this quantity approaching as I do this? Let's look at a few more examples with some graphs just to get a better idea. Okay, so here we are with one of my favorite examples, all right? This is arctan x. This is the inverse tangent function. Sometimes you'll see this written tan with a superscript -1. It's the same thing. It's just a different way of writing it. And arctan is a really great example of an interesting limit at infinity. If we let x go to infinity, what is the height of this graph tending towards? Well, let's let x get bigger and bigger and take a look. As I let x get bigger and bigger and bigger, I see that the height of this curve is getting closer and closer to pi over 2. It never actually gets there, but it gets closer and closer and closer. And so that's what we mean when we say the limit as x goes to infinity of arctan of x equals pi over 2. Okay, let's go back to the origin here. And let's go to the other side. What about the limit as x goes to negative infinity of arctan of x? Well, let's see what happens there. Well, it's a negative value. Now, the way I've got my video recording thing set up, you can't see the right-hand side where the axes are labeled. Let me drag it over. There you go. You can see that it's approaching negative pi over 2. Now, it never actually gets to negative pi over 2, but it gets closer and closer and closer. In fact, we can get it to be as close as we want just by making x negative enough, right? So that's what it means for the limit to be negative pi. The limit as x goes to infinity to be negative pi over 2. So that's a cool function. Now, there's a few functions that we're going to want to keep in mind. They will help us make computations when we have to compute limits. And one of these is 1 over x, all right? What would the limit as x goes to infinity of 1 over x be? Well, as I let x go to infinity, you can see that 1 over x is going to, well, the graph is just getting less and less and less and less. It's getting smaller and smaller, and so it's going to 0. And that should make intuitive sense, right? Because I'm dividing by x. So if I let x get very big, 1 over x is going to get very small. When x is 10, I have 1/10. When x is 100, I have 100th. When x is 1,000, I have 1,000th. When x is 1,000,000, I have 1/1,000,000th. It's really tiny, right? The bigger this gets, the smaller this gets. So it makes sense. And it works for negative values of x as well, right? It's always negative, but it's approaching 0. So the limit as x goes to negative infinity of 1 over x is also 0, all right? We can talk about 1 over x squared, and of course that'll do the same thing because, again, when x gets large, right, when x goes to infinity, 1 over x squared, well, x squared is going to get large, and so 1 over x squared is going to get small, right? So it also approaches 0 when x goes to infinity or negative infinity, and you can see that here. What about 1 over root x? What do you think that would do? Well, also goes to 0, right? Because the square root of x, as x goes to infinity, as x gets big, the square root of x is going to get big, right? It gets large. And if the denominator gets large, the fraction is going to get small, right? Provided that the numerator doesn't change, right? So 1 over square root of x goes to 0 as well. And you don't see a graph to the left, of course, because you can't plug in negative values for x here. Now, what about just square root of x? What if I just wanted to take the limit as x goes to infinity of root x? What would that do? Well, now I'm not dividing, right? And like we just said, when x gets big, square root of x gets big, right? It's, square root of x is always significantly less than x, but it grows nonetheless. And so if I was asking, what is the limit as x goes to infinity of square root of x, the answer would be infinity. It just grows and grows and grows. It doesn't approach any one number, right? So the limit as x goes to infinity can be infinity, or sometimes it can be a particular number. I'm going to throw in one more example. Just came to mind. Let's look at sine x over x. This is a fun one. And you can see it's a little less trivial. It's wobbling, right? It's wobbling up and down. And if we zoom in, you can see it's always wobbling up and down above and below the x-axis, but it is getting closer and closer and closer to the x-axis, right? And so the limit is still 0, right? So the limit as x goes to infinity of sine x over x is 0. It's getting closer and closer to 0. And you can reason that out, right? The denominator is getting bigger and bigger and bigger as x goes to infinity, but the numerator is always between -1 and 1. We know that about the sine function. So the numerator is not really getting big, but the denominator is, and so the result is that the whole expression will be getting small. Okay, let's look at a problem-solving example. We want to compute the limit as x goes to infinity of this expression here. Okay, so the idea here is we're going to actually use a trick, all right? And the trick for doing these is we're going to divide through by the largest power of x. And that largest power of x that I see is x squared, all right? So if I divide everything through by x squared, what do I get? All right, I get this. Now, there's some things that cancel, right? So the x squareds cancel here, the x squareds cancel here. This x cancels with that square, just leaving me with an x in the denominator. And so I have this expression here. Okay, so why did that help? Well, because of what we just observed in the graph, right? We know that as x goes to infinity, a quantity like this is going to go to, yes, 0, right? Because the denominator is getting really big, but the numerator is not. And so this expression here is going to 0. Okay, 3 is a constant. When x goes to infinity, 3 stays 3. So its limit is 3, right? So it just stays 3. Same with 6. But this one over here, we're dividing by x. When x goes to infinity, when x gets very large, 7 over x gets very small. It goes to 0. We saw that in the pictures. And the same thing for this one. This goes to 0. So we can see that we're using properties of limits. I mean, we know that limits can, if the limit of the numerator exists and the limit of the denominator exists, you can do these limits separately, and then you can do these separately. So we're breaking down this limit into pieces. So we are using properties of limits, but I'm doing them kind of, I'm kind of hiding that under the hood here. So what do we get here? Well, this goes to 0. That stays 3. This is 6. That goes to 0, and this goes to 0, right? So what am I getting here? I'm getting -3 over 6. Well, that simplifies to -1/2. So the limit as x goes to infinity is -1/2. And here's a picture of the function that we were just looking at. And If you look as x goes to positive infinity here, you can see that the graph is getting closer and closer to this value here, which is -1/2, right? So we have verified that analytically and by looking at the graph. And another example here, we're taking the limit as x goes to infinity of this expression. So what are we going to do? Same idea. We're going to divide through by the highest power of x, which in this case is x cubed. And let's see what happens here. Well, x cubed divided by x cubed is 1. X divided by x cubed is 1 over x squared. X squared divided by x cubed is 1 over x. And x divided by x cubed is 1 over x squared. Okay, so where are these going? Well, this is just staying 1. It's a constant. This is going to 0 because x is getting big and it's in the denominator. This is going to 0, and this is going to 0. And so in the limit, now I hesitate to write equals something here, and you'll see why in a second. Look what's happening. The denominator is going to 0, right? This is going to 0, this is going to 0. I'm subtracting them, so their difference will be going to 0. Now the numerator is not going to 0. It's going to 1 plus 0. It's going to 1. So if the numerator is going to 1 and the denominator is going to 0, what's happening here? Well, I'm taking a number and dividing it by something that's getting very, 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 very small. The result gets very, very, very big. So what's happening here is that this thing is not getting close to any one number. It's actually blowing up to infinity. Now, the only question is it going to positive infinity or negative infinity? Well, when x is large, 1 over x squared is smaller than 1 over x because I'm dividing by a bigger number. And so the denominator will be positive, and the numerator is always positive because all these things are positive. And so the quantity will always be positive. And so it must be going to positive infinity. And by the way, if you didn't believe me about that thing, or if you didn't understand what I was saying about the denominator, you could just work it out. 1 over x minus 1 over x squared, get a common denominator here. Oops. Right? Combine these. And then you see when x is large, okay, if it's less than 1, this can be negative. But if it's bigger than 1, it's not, right? And x is going to infinity, so it will eventually be bigger than 1. Right? So this is going to be positive for large values of x. And the denominator is positive because it's squared. So this is always positive. So that's what I was saying about the denominator. The denominator is always positive. Numerator is always positive. So if I had to choose between plus or minus infinity, I'm going to choose positive infinity here. And here's the graph of our function. And you see as I go off to the right, if I go off to the right, you can see the graph is just growing and growing and growing. It's not going close to any one particular number. It's just going up and up and up and up. It's going up to infinity. And so that verifies what we got. Okay, I want to point out something else about this function, though. All right, we determined the limit was infinity, but I think that we can say something a little bit more interesting about it. If you look at the behavior of this, it looks like it's resembling a straight line. In fact, it looks to me like this is resembling the line y equals x plus 1. Look at this. The line y equals x plus 1 and the graph look almost identical. They're really close to each other. So how do we describe this behavior? And by the way, this is what we call a slant asymptote. Y equals x plus 1 is an asymptote for this graph. An asymptote is a straight line that the graph gets closer and closer to for large values, that the graph approximates. So how would we show that this line is a slant asymptote for this function? Let's go to the paper and see if we can do that. Well, what we were seeing is that the difference between the line and the graph of the function and the line was getting less and less and less. They're approaching each other. But what I just said is the key to what we need to do. The difference is approaching 0. So what we'll do is we'll look at the limit as x goes to infinity of our function. This is the function we were graphing, and we want to look at the difference between that and the line that we think is the slant asymptote. And I want to know, is this going to 0? So let's compute this limit and see if we can do that. Well, okay, to do this limit, I think we want to combine these, right? So let's get a common denominator. So I'm going to multiply the numerator and denominator of this guy by x squared minus x. And when you do that, if you multiply this times x squared minus x, and you should work this out as an exercise for yourself, you'll see that you get x cubed minus x, right? So this limit's the same as this limit. But now we can combine these fractions, right? Because they have a common denominator. Okay, so when I combine them, I get x cubed minus x cubed, so those cancel off. And I have x minus negative x, right? So that is 2x. Oh, so that's just equal to this. What's this limit? Well, we can compute this limit by dividing through by, as we were doing, the largest power of x squared. Right, so we'll divide everything by x squared here. And what happens? Well, the x cancels with the x down here. I get 2 over x in the numerator. The x squared and the x squared cancel. I get 1. This x cancels with one of those x's. I get 1 over x. Now, what are these going to? Well, I'm dividing by x, and x is going to infinity, so this is going to 0. Dividing by x, x is going to infinity, so this is going to 0. This is just staying 1. So this whole quantity is going to 0 over 1 minus 0. Well, 0 divided by 1 is 0. So we have verified this fact, right? That the difference between these two functions is approaching 0. And that means that these functions are resembling each other for large values of x. And that's what we're seeing in the graph. The difference between the red line and the blue curve is going to 0 as x goes to infinity. And that's what it means to be a slant asymptote. And so this is how you verify that something's a slant asymptote. You subtract it from the function and and show that the limit of the difference is equal to 0. Now, if we go back, I want to point something out here. If we go back to the other functions we were looking at, with our earlier function over here, we looked at this one. Here, the line y equals negative 1/2 is our asymptote, right? And that's just equal to the limit of the function, right? The limit of this function here is negative 1/2, and so y equals negative 1/2 is a horizontal asymptote. If I take their difference, the limit of the difference will go to 0. And in our first early on example, we had arctan x. We saw that its limit was pi over 2, and so pi over 2 is an asymptote. Y equals pi over 2, the horizontal line. It actually has 2 asymptotes. We also have y equals negative pi over 2 over here. So if the limit of the function is a number as x goes to infinity, then y equals that number is a horizontal asymptote. But we can also have slant asymptotes, diagonal asymptotes, and as we showed, you can show that they're slant asymptotes by taking the difference and showing the limit goes to 0. Okay, so that's limits at infinity. So I hope you learned something, and I'll catch you in the next video.